Most people doing intermittent fasting are waiting for hour 16, like it's some kind of finish line. They've heard the phrase fat burning kicks in after 12 hours so many times it's basically gospel now, and they have no idea they're already missing the most important metabolic event happening inside them 2 hours before they think anything real starts. The switch doesn't happen at 16. It doesn't even happen at 12. It happens around hour 14 in your liver, and it is not a gradual fade. It is a hard pivot. Your body has been engineering this pivot for millions of years, and almost nobody is talking about it specifically. In the next few minutes, you are going to understand what your liver is actually doing at that exact window, why it matters more if you're over 40, and why the information floating around fasting communities is stopping people from understanding what they're actually achieving. Your liver is the most metabolically underestimated organ in your body. People think about it in terms of detox and alcohol, but your liver is running an extraordinarily complex fuel management system every single hour of every day. Think of it like the city's central power grid, constantly balancing supply and demand, routing energy to where it needs to go, switching between fuel sources depending on what's coming in. When you eat, your liver takes in glucose and packages it as glycogen, essentially tying the energy into storage bundles it can unpack later. A healthy liver holds somewhere between 80 and 120 grams of glycogen at full capacity. That sounds like a lot until you understand the demand against it. Your resting metabolic rate and your brain's glucose demand alone. The brain consumes roughly 120 grams of glucose per day. Will drain that reserve faster than most people appreciate. A study published in the Journal of Clinical Investigation found that liver glycogen depletion under fasting conditions follows a steeper curve than muscle glycogen, with meaningful depletion beginning well before the 12-hour mark in metabolically healthy adults. By hour 10, your liver is drawing down. By hour 12, it's operating on reserve. And by hour 14, something fundamentally different begins. Here is what happens in your liver at that specific window. And this is the part that the generic fasting content never breaks down precisely. As glycogen levels approach near depletion, your liver receives a biochemical signal shift. Insulin, which had been present in low but still suppressive concentrations, continues to fall. And as insulin drops below a critical threshold, it stops blocking a key enzyme pathway, the one that governs gluconeogenesis. Gluconeogenesis is your liver synthesizing brand new glucose from non-carbohydrate substrates, lactate, glycerol, and certain amino acids. This is not fat burning yet. This is your body keeping your blood glucose stable using raw materials it's pulling from other systems while it prepares the next phase. The liver essentially becomes a manufacturing plant instead of a warehouse. It's no longer unpacking stored glucose. It's building new glucose from scratch to keep your brain and red blood cells supplied. This transition is the glycogen switch, and most people have no idea it is running inside them. But here is where it gets significantly more interesting, because gluconeogenesis and the next phase happen in parallel, not in sequence. As insulin drops into that critical low zone around hour 14, AMPK activation begins to rise. AMPK, adenosine monophosphate activated protein kinase, is sometimes called the cellular energy sensor, but that description undersells it. AMPK is closer to the executive function of your metabolic system. When it activates, it initiates a cascade that includes the upregulation of fatty acid transport proteins in the liver, the suppression of lipogenesis, and, critically, the activation of carnitine palmitoyltransferase 1, the enzyme that shuttles long-chain fatty acids into the mitochondria for oxidation. In plain terms, AMPK activation is what opens the door for fat oxidation to actually begin in the liver. And when fatty acid oxidation accelerates inside hepatic mitochondria, the byproduct is acetyl-CoA. And when acetyl-CoA production exceeds the liver's capacity to run it through the citric acid cycle, the excess gets diverted into ketogenesis. Your liver starts producing ketone bodies, beta-hydroxybutyrate, acetoacetate, acetone. This is not happening at hour 16. This is beginning at hour 14 in people whose insulin sensitivity allows that threshold to drop in time. And here is the detail that almost no fasting video mentions. In adults over 40 with even mild insulin resistance, that AMPK activation threshold requires insulin to fall further before the switch engages, which means for a significant percentage of people doing 16/8 fasting, the metabolic shift they are chasing is barely beginning right as they break their fast. Research published in Cell Metabolism in 2023 showed that individuals with elevated fasting insulin required on average 1.8 additional hours of fasting to reach equivalent AMPK activation levels compared to insulin-sensitive controls. That is not a small gap. That means a 43-year-old with subclinical insulin resistance doing a clean 16-hour fast is getting roughly the equivalent metabolic stimulus at hour 16 that a metabolically healthy 28-year-old gets at hour 14. The window is not universal. Your liver's pivot point is personalized, and it is tied directly to your insulin sensitivity, and it gets even wilder when you trace where those ketone bodies actually go. Beta-hydroxybutyrate is not just a fuel source, it is a signaling molecule. Once it enters circulation, it crosses the blood-brain barrier and acts as a direct substrate for neuronal energy production. But it also inhibits NLRP3 inflammasome activity, which is one of the primary drivers of systemic neuroinflammation associated with metabolic aging. A study in Nature Aging from 2022 found that even modest elevations in beta-hydroxybutyrate, the kind produced during a 14 to 16-hour fast, were associated with measurable reductions in inflammatory cytokines, including IL-1 beta and IL-18 in middle-aged adults. Your liver producing ketones is not just a sign that fat oxidation is happening. It is actively sending anti-inflammatory signals to your brain. The liver's metabolic pivot at hour 14 is a whole-body communication event, not just a local fuel switch. Now here's the part that should make you genuinely frustrated, because this information has been sitting in biochemistry literature for decades. And what you've been fed instead is a simplified, vague, marketable version of fasting science, designed more to sell fasting apps and branded electrolyte powders than to actually explain what your body is doing. The supplement industry has a very specific financial interest in you, believing that fasting is complicated, fragile, and requires products to optimize. They want you to buy a glucose monitor, a ketone breath meter, a collagen powder to take at hour 13, an exogenous ketone drink to jumpstart ketosis, all of it engineered around a version of fasting science that is deliberately kept surface level, so the gap between what you know and what you need always gets filled by a product. The reality is that your liver has been executing this glycogen to gluconeogenesis to ketogenesis sequence since long before the word biohacking existed. Your ancestors were not doing structured 16/8 windows. They were going 14, 16, 20 hours between successful hunts or harvests, and their livers were running this exact cascade without a single supplement. Your DNA is literally constructed around this metabolic rhythm. Glycogenolysis and gluconeogenesis are not stress responses, they are your design. The modern food environment buried it under a constant insulin-spiking eating pattern that never lets the switch engage, and the wellness industry profits from the confusion that creates. So here is exactly what you can do with this information, practically and specifically. If you are currently doing a 16/8 fast, and you are over 40 or suspect your insulin sensitivity is not optimal, the single most effective adjustment you can make is extending your fasting window to 18 hours, 3 to 4 days per week, rather than 16 every day. The additional 2 hours meaningfully increases the probability that your liver completes the gluconeogenic phase and moves into sustained ketogenesis before you eat. You do not need to do this daily. The metabolic adaptation compounds over time, and chronic daily extended fasting without variation can actually blunt the adaptive response as your body anticipates the pattern. Variation is a feature, not a flaw. If you are newer to fasting, a 14-hour window is already doing more than you think, and the priority at that stage should be what you eat to break that fast. A meal that is low glycemic index and moderate in protein, rather than a high carbohydrate meal that spikes insulin immediately and cuts the AMPK signal short. Eating 40 to 50 grams of protein with healthy fat and fiber within the first meal of your eating window supports gluconeogenic substrate availability for your next fasting cycle, while minimizing the insulin overshoot that would suppress the very pathways you just spent 14 hours activating. the sequence matters as much as the duration. There are two additional practical levers that most fasting content completely ignores. The first is eating window timing. Your liver's enzymatic activity for glycogenolysis and gluconeogenesis follows a circadian rhythm. The enzymes involved are more active in the morning and early afternoon than in the evening. A fast that ends at noon is biochemically different from a fast that ends at 8 p.m., even at identical durations. If you are doing a 14 or 16-hour fast, ending it in the late morning or early afternoon rather than in the evening aligns your break fast with your liver's peak gluconeogenic efficiency and produces a more complete metabolic cycle. The second lever is the evening meal composition the night before. A lower carbohydrate dinner, one that does not fully replenish liver glycogen, means you enter your overnight fast with a partial glycogen deficit, which moves the hour 14 switch closer to hour 12 for your specific biology. That is not calorie restriction. That is just strategic substrate management. If you have any history of hypoglycemia, are on diabetes medication, or are pregnant, speak to your physician before adjusting or extending your fasting windows. Your baseline glucose regulation needs professional oversight before any protocol changes. For everyone else, add morning light exposure within 30 minutes of waking, because circadian entrainment directly influences cortisol and HPA axis activation patterns. That set the pace for gluconeogenesis timing in the early fasting window. Free, requires no subscription, and it compounds every single day. Here is your challenge, and it costs you nothing except time you are already spending asleep. Try an 18-hour fast 3 times this week. Not every day, 3 times. Break it with protein and fat, not a bowl of cereal or a piece of toast. Do it for 10 days consistently and come back to this video and drop a comment telling me what changed. Your energy in the morning, your mental clarity before you eat, your hunger patterns, whether the 2 p.m. crash you used to rely on coffee for just quietly disappeared. The comments on videos like this are genuinely some of the most useful data you will find anywhere on this topic, because these are real people running real unsponsored experiments on their own bodies and reporting back honestly. The next video is going to take this further, specifically what happens to visceral adipose tissue during sustained AMPK activation, and why the location of your body fat determines how quickly you respond to any fasting protocol at all. That one is going to reframe everything you think you know about where fat actually comes from and where it actually goes first. For now, remember this. Hour 14 is not a waiting room for hour 16. It is the main event. Your liver knew that all along.